So here we're getting ready for the next section in Calc 2, the final chapter in Calc 2. 13.1 is curves in space. Now I couldn't help but to look at this title and think of one of my all-time favorite skits from one of my all-time favorite TV shows. That would be The Muppet Show back in the 70s, late 70s, early 80s, I think it was. Anyway, they had a little skit called Pigs in Space. And of course, Miss Piggy was a star, and it's all about, like, it was kind of like a Star Trek pigs in space, really. But it made me think of another. So here, yeah, we'll write this down. Where's my thing? Oh, it's not plugged in. We're not off to a good start so far. But it made me think of another of my favorite shows, narrated by one of my favorite people. That being, so here we are, 13.1. And this is going to be curves in space. Similar to Pigs in Space, but math instead of comedy. But another of my favorite, we'll start with a sidebar right away. One of my favorite shows when I was a kid was this show called Wild America, and it was hosted by this guy named Marty Stauffer. Now, Marty Stauffer, he was from Arkansas originally, but he went on, he moved to Alaska and started making wildlife films. And he'd always, start the intro with something like, good evening, ladies and gentlemen. And he had this little southern drawl. Today we're going to see a film on the tree fox and its relatives. Now, the tree fox is a wily little creature that roams most of the tundra of Canada and southeast Alaska. And, life is always a challenge in this area, and today we're going to learn all about its struggle for survival. Tonight on Wild America. And then I get into this dramatic music. And I thought, wow, I want to grow up be like Marty Stauffer. But instead I grew up to make math videos. But I at least get to narrate my own math videos. And I don't have a daughter. I have a son instead. And I got a beard sometimes. And I don't know what these creatures are, but I don't have any of them either. So this is Marty Stauffer and from Wild America. I don't know why I felt like this tangent. But I thought it was important to share Wild America. So anyway, back to curves in space. Let's do a quick little review. In chapter 11, one of the topics we touched on was parametrics, right? Where we kind of broke x and y apart, and as a function of some third parameter, oftentimes we called it t. And then in chapter 12, what did we do? We learned about lines and planes in space. In 3D space. And we talked about vectors. And so the next logical step is chapter 13, where we're going to talk about parameterized vector equations in 3D space. Remember, this is just three real axes, and that's a short way to write 3D space. Now, if you look at this, parameterized vector equations. Holy cow! Well, I think we'll see that it's really a pretty logical step from where we've been. So let's quick review these. What a parameterized equation is. We said that we could do x equals some function of t. Y could equal some, let's see, g of t. And that's not supposed to be a hatch or anything there. That could be confusing. And then we could say that z is some third function, h of t, right? And so this is how we parameterize some equation. So we know x is a function of time, y is a function of time, and z is a function of time. And then we could also say this point in space a point in space, P would then be XYZ, but we know that P XYZ really equals F of t, G of t, and H of t. So this could also be our point. All right. Now what we're going to do with this point, for this point P, we're going to define a position vector. Define a position vector. And so to define a vector, we need 2 points. So we're going to start from the origin to the point. And for that, we're going to say that it's this vector OP. And that is the same as a vector we're going to call R. Now you think you'd call it P for point, but R really is kind of a generic term for position. And it's really the radius from the origin. So it's the R vector, and that's going to equal F of t I hat plus G of t j hat plus H of t k hat. So what did we do? Nothing too complicated yet. All we've done is say we have a point xyz. This point is some function of time, so we can break it down, parameterize it, f of t, g of t, h of t. And we've now drawn a vector from O to P, from the origin to the point, which we're going to call R for radius. And then that'll be f of t I. So this is the x-coordinate times the unit vector in the x direction, g of t j, h of t k. All right, so this is all good so far. And let's throw in a couple examples of what these might look like here. So we've got, not Marty Stauffer, we've got example of curves in space. This will fit in here nicely. We'll put that right there. Perfect. So here we've got a few, and I know these are hard to read, but for instance, this one here is R of t, so the position vector based on time is sine of 3t times the cosine of t times I plus sine of 3t sine of t j plus t of k. All right, and that makes this kind of squiggly line. Here's another one, cosine of t times I, sine of t j, right? So cos t I, sine t j, that would make a circle. But then it goes sine of 2tk, so it also oscillates. Instead of just going in a circle, it kind of goes up and down and up and down and makes this saddle-shaped thing. Likewise, there's a really long one, complicated, but it makes this kind of spiral that goes all around. Now these may seem crazy, but when you think of things like electron orbitals and electrical fields and flux lines, if you had a kind of a toroid coil and there's some flux that goes around it, these shapes are all very real shapes that you could encounter in the physical world. So let's come up with our own slightly more simple example. Now I usually try to avoid doing exactly what the book does, but this is the classic example that I think is the easy one to look at. So let's look at this example, and I'm going to say that R of t equals, we'll say cos t I plus sine t j plus just t times k hat. Okay, so let's, first of all, let's notice that this is a vector function, and I'm going to highlight some of this stuff in blue here, light blue. So this is a vector function. Vector function of a scalar parameter. Right? Time, t, and usually we refer to t as time, and that's one of the most common parameters. Doesn't have a magnitude, doesn't have a direction, it's just time. It's not a vector. But we've got a vector function that uses time as a parameter. So if we look at this part over here, let's think about what does this do? What shape does this make? We've got cosine times I, so the cosine of the time is really determining our x position, and the sine of the time is really is really determining our y position. So what does this thing do? This makes a circle, right? It just goes looping around in a circle. But then we've got this thing here, right? What does this do? So as our particle travels around in a circle in the xy plane, this thing over here, the k component, the vertical component, if we think of it that way, so as time increases, its vertical position will increase. So what's this going to make? It's going to make like a coil, right? It's going around and around in a circle, but it keeps going up because of this k component here. So let's take a look at some examples of that. I have some pictures of this too. And I think we call that coil springs. We put that in there, perfect spot. Yeah, right there, looks good. And so if you can see this, this is the one we just plotted. Cosine I plus sine of t j plus tk, right? So it starts wherever, and then actually it starts right here, and then it goes around and around, but as it goes around, it also goes up, right? Well, how could we change this if we said cosine ti plus sine tj plus 0.3 tk, so we can scale the t part of it, or the k part of it, the vertical growth, we can slow down the vertical growth. So for every lap, it only goes up 0.3, or for every period, it only goes up 0.3 of the time. Likewise, we can speed up how fast it goes around by changing this part of the argument here, the cosine of 5t, the sine of 5t. These are also in your book too. And then it continues to go up at the same rate, but we spin a lot faster. So there's a lot of knobs and dials to turn to make these things do what we want them to do. All right. Now, I debated about some of the mathiness of the next couple of parts, but I've got some kind of mathy definitions I usually like to avoid, but I'm going to throw them in here anyway. So let's, in here, stick this picture of the definition of a limit. All right, and we'll see if this looks familiar at all. Slide this guy down. Okay, so what does it say? Definition: let r of t, vector r of t, so this is a vector function of t, f of t I, g of t j, h of t k. We've done this before. Be a vector function with the domain d. L is a vector, right? We say that r has the limit L as t approaches t sub 0, t naught, and write limit as t approaches t naught of r of t equals L. If for every number epsilon greater than 0, there exists a corresponding number delta that's greater than 0, such that for all real numbers, whatever, that this stuff remains true. What does this mean? That as we, make L closer and closer and closer, or as close as we want our position vector to be to some L, right? The distance between the position vector and our target L gets smaller than epsilon. I can find some t, some parameter that gets closer and closer, so it's less than delta. So if I said, yeah, I need to be this close to L, I can say no problem. I just got to make sure that my parameter is this close, is less than delta away from some other value t. Right? Then we can say that the limit of the position vector as t approaches this thing becomes L. So this is just like the old-fashioned limit you learned in Chapter 2 of Calc 1, so a long time ago. But it's important to think about the analogy between vector functions and just regular scalar functions like we've talked to up to this point. All right, kind of a mathy definition, but important. All right, next one. I got to switch over to black before I forget. We're going to insert what continuous I was going to stick in here next. Yeah. We'll put that in here. That's as high as I can go. Okay, definition. A vector function r of t is continuous at point t equals t0 in its domain if the limit of r of t equals r of t0. Right now, we've pretty much taken this for granted in all the stuff we've done so far, but if we get closer and closer to t sub 0, the limit of this vector becomes r of that position itself. All right, so that's, again, something we covered in Chapter 2 of Calc 1, but this determines if a function is continuous. So for instance, if I had some function here, but there's a hole here, but my actual value is up here, right? This would be not continuous, right? So this is, I'm going to make this red. This thing is not continuous, right? Because as I approach, the limit as I approach this t naught here is not the same as the value, right? So this is an example of discontinuous. All right, so let's go. Let's get back to the real conceptual stuff here. And I'm going to draw a coordinate system, and I'm going to draw it like this, and like this, and like this, and we'll say this is. I'm going to call this one x, call this one y, and call this one z here. And then I'm going to take some particle. I'm going to make my particle p. It's just going to kind of cruise along some path in 3D space. Maybe like this. Okay. Now I could draw a position vector at a certain time. And I'm going to draw this position vector like here. So remember, the position vector would go from right here. I'm going to say that this vector is r, the vector r of some time t. All right. And I'm going to kind of increment forward in time. I'm going to draw another position vector that goes out here to some other time. So some other point, I'm going to call this point P. I'm going to call this point Q. And then this vector, since it happens a little later in time, it's still a vector, r vector, of t plus delta t, right? Well, I'm going to draw a third vector in here, and this is going to look pretty familiar. And this vector is going to go from P to Q. And so this is vector PQ. But what do we notice about this? It goes from the tip of the one vector to the tip of the other vector. And another way to write this, since it goes from tip of one vector to the tip of another vector, this looks a lot like our non-intuitive subtraction vector. So this is the same as r of t plus, get out of there. No, I did not want that. I want that. T plus delta t minus the vector r of t. So this is really the difference between these two vectors. Okay, so we've got this thing. If I think of this as, and it may start to smell fairly familiar to you guys, if we think of this as kind of a position and velocity, and then so the velocity, the average velocity, right? The average velocity would be the vector PQ over, right, how long did it take? Well, that equals, as we just determined up here, the position vector t plus delta t minus the position vector at t all over delta t. Now this should be looking very, very familiar because this looks a lot like our definition of the slope, right? So as we made delta t smaller and smaller and smaller and smaller, we might wind up with some tangential vector there that is in the same direction. So it's the instantaneous direction, or we could even say the instantaneous velocity of this particle at time t. And we could do this out. Let's see, how can I do this? I'm gonna go to another page. I'm gonna actually write this out. If I have time, I'll put in a way to skip over this. But if we've got, I want to write this in black, back to our original stuff here. I've got the vector t plus delta t, which really will equal f of t plus delta t I plus g t plus delta t j plus h t plus delta t k, and then I subtract from that this other thing, right, which will just be r of the original, the original time position vector at time t, which equals just f of t I plus, you know, all that stuff. You can fill that in if you want. Well, that will equal the, we can you know, subtract these two I components here, f of t plus delta t minus f of t I plus this other stuff here. And if we divide this whole thing by delta t, divide each component by delta t, right, what will that give me? It'll end up leading to the dr of t dt will equal these individual, because if I look at this, f of t plus delta t minus f of t divided by delta t, well, that's the derivative of just our individual functions. So this gives us df dt I plus dg dt j plus dh dt k. Right, now, this may seem obvious. It may seem pretty obvious that the derivative of the vector, you know, the derivative of this vector equation, which is vector equation here, right? Vector equation. I'm going to circle that. That's important to notice, so I'll do this kind of in yellow for no other reason than I haven't used it yet. This is a vector, you know, breaks down into the individual parameters, the individual components, those individual derivatives. So that allows us to do some very nice things pretty easily by looking at it this way. All right, so, but again, if we think of this also in terms of velocities and positions, the derivative, the time derivative of position, what is that? That is velocity of time, right? Okay, now there's a list of rules in your book of some special rules, but so rules of vector differentiation, right? The basic ones are scalar, sum, difference. You know, all those kind of ones, right? Where the vector, you know, the derivative of the sum of two vector equations is the individual ones. If you multiply it by some scalar, you can just take the scalar out of the derivative. The difference between, you know, the two derivatives is the same as the difference of the derivatives themselves. That kind of thing. But there's, when we get into the product rule, that gets interesting, right? Right, because when I say product of two vector equations, the product of two vectors, well, we have two ways to do that. So I'm going to write two different ones. If I take the time derivative, or ddt, of u dot v, what will that equal? Well, it turns out it's the same as the product rule before, so we say first times the derivative of the second, so it's u times dv dt plus the derivative of the first du dt times the second. Right. Now, since, and this is a dot product here, that's important. Dot products are always tough to draw because it wants to give me the menu. So that's the product rule as opposed to dot, as it applies to dot product. If we do the same thing for the cross product, the ddt of some u function crossed with some v function, well, it may come as no surprise that this will be the first crossed with the derivative of the second plus the second, or the derivative of the second, du dt, crossed with the first. Now, this becomes important because we can't, when we did this with scalars, right, u dv dt, or, dv dt times u, whatever, the same thing. But remember, with cross products, it makes a big difference, the order. So you have to remember, order matters. Why? Because cross product does not commute. All right, order matters. The cross product does not commute. So this matters here, and this order matters here. Okay, so as you do some of these homework problems, you got to keep that in mind. All right, now we're going to skip to an example. Not skip to an example, it's time to do an example. And if you want to skip the example, I'll hopefully have time to put a link in to jump forward in this. Let's say we've got some position vector, right? A position vector function that equals e to the negative t I plus 2 cosine of t j plus 2 cosine t. Oh, nope, I made a mistake there. Let me fix this. I was trying to do this by memory and it didn't work. 2 cosine of 3t j plus, and this one is also 2 sine of 3t. 3t. Okay, all right. Well, before we dive into this, well, the problem will be to find v of t and a of t. Right, well, we determined earlier that the velocity of as a function of time is the derivative of position. Well, a is acceleration, right? Second derivative of position, or the first derivative of velocity. And we also want to find speed and direction at t equals 0. Okay, so our initial speed and our initial direction. But before we get into that, I want to take a little time to think, right? It's always good to think about this. Let's look at this one over here. What does this do? What does that do? And then what does this do? Okay, well, cosine 3tj and then sine of 3tk, that seems like it should make a circle, except instead of making a circle in the xy plane, it's going to make a circle in the yz plane. And we've got these 2's here, the leading 2 here and the leading 2 here. So that means the radius of the circle is not going to be 1, but the radius is actually going to be 2. And we've got this parameter 3 here, or this scaling factor 3, which means we're going to go around 3 times as fast. So it won't take us 2 pi seconds or minutes or whatever to make it all the way around the circle. We'll do that in 1/3 the time. So it's going to go fairly fast, 3 times as fast, around in a circle in the YZ plane, and it's going to have a radius of 2. All right, so this part just goes around and around in a circle. So this is a circle. What does this do? Well, when time equals 0, this will just be 1, so it's going to start out at an x position of 1. But then as time increases, this negative exponent here will make this thing approach 0. So it's going to start out at 1, and it's going to come back to 0. And it's never going to actually reach 0, but it's going to start out 1. At first, it's going to be going pretty fast, and it's going to slowly approach 0, never reaching 0. So it's going to look like a partially coiled spring, or a spring that's compressed very much near the origin, but then stretches out as we get out towards x equals 1. The helix, the coil, is going in the YZ plane. All right, so anyway, if that doesn't make sense to you, let's talk about it more in class. The velocity, so to actually solve the problem as a function of time, is just the derivative of this, right? Well, what's the first derivative? It's negative e to the negative t times I, right? That's easy. 2 cosine of 3t, the derivative of cosine is negative sine. So, and we have to do the chain rule here, right? There's a 3 there. So that becomes negative 6 sine of 3t, and that's our j component. And then finally we have the derivative of sine is cosine, positive cosine, but we have to do the chain rule here. So it's going to be plus 6 cosine of 3t, and that is our k component. All right, so that's our vertical component. So velocity, okay, got that. Acceleration is the derivative of this again, so that becomes positive, equals e to the negative t again, I. And then derivative of sine is cosine. We have to do this one more time, chain rule, so that it remains negative. Now it's 18 sine, oh, nope, 18 cosine. Cosine of 3t j. Derivative of cosine is negative sine, so this also becomes negative. Negative 18 sine of 3t, and that's still the k component. All right. So now I've got the velocity and acceleration. I'm going to make the important note here that v of t equals dr of t dt, and that the acceleration as a function of time equals the derivative of velocity of a function of time over dt, which really equals the second derivative, so it's d squared r of t over dt squared. Okay, so for those who have taken physics, this makes a lot more sense. For those who are, this is new, if this is confusing, like what the heck is all this about velocity, acceleration, time, blah, 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 ask about that in class. But still, we're supposed to find the speed and direction at t equals 0, the speed and direction. So if we take v of t and we plug in where did I do this? Okay, so speed at equals 0, which is really the magnitude of the velocity at 0. Okay, so if we plug a 0 in for here, let's see, negative, well that's 0, so that's 1, so it's negative 1. So that becomes just negative I, and then the sign of 0 is 0, so that goes away, so let's just add a plus of 0j. And then if we look at this, the cosine of 0 is 1, but 6 times that, so it's 6 times 1 plus 6k, right? But really I still wanted the magnitude. I'm just interested in the speed, so I take the magnitude of this, and that equals 1 squared is 1, 0, 6 squared is 36, take the square root, that becomes the square root of 37. So our initial speed is the square root of 37. Whatever the units are, we don't know. But the direction becomes the unit vector of our velocity. So this really becomes like v hat of 0, which equals negative 1 over root 37i plus 0, and then plus 6 over root 37k. So that's the direction, which is the unit vector of the velocity. All right, so we're good there. Good. All right. Moving on, we need to look at one important concept that I think is pretty important, and that is smoothness. And so a 2D function is smooth if it is always differentiable. Right, so there, that means no cusps, jumps, holes, etc. Right? So a curve in 3D is smooth if, first, it has to be differentiable. And dr dt, dr, the position vector dt, is never equal to 0. Right? Now this is, notice this is important, this is 0 vector. So that's 0 vector, which is 0i plus 0j plus 0k. Right, now why is this? Why can the derivative never be 0? I mean, we spend half of the first semester calculus looking for places where the derivative is 0. But the problem is with a 3D curve, if we have some point at which the derivative, all three components of the derivative, we hit a 0 vector derivative. So I could be cruising along here like this, and all of a sudden I slow down and I come to a complete stop. And I can take off in some other totally different direction. Right? That becomes a cusp, or a complete stop. And take off in a different direction. Right, that's this thing right here. So I can't do that. If I do that, it's no longer smooth. And one of the reasons that that doesn't work, if I try to draw a tangent, let's say I try to draw the velocity here, you know, that could be tangent, you know, that could be tangent. You know, there's all these various tangents at this point, so that it doesn't have any velocity at that point. I don't know which direction it's going. I know its speed is 0, but I don't know which direction it's going because it's simultaneously all components are 0. All right, So, speaking of tangents, so the tangent to the curve in 3D, right? We need two things. We need a point, and the point will simply be f of whatever time it is, g of whatever time it is, and h of whatever time it is. But I also need a direction. And the direction, remember, is the derivative. So that could either be v of t naught, or it could be a unit vector, so v hat of t naught. Or, in other words, we could write that as d position dt. Okay, so it could be any one of those. And that would be the tangent line. So the last thing I'll do here, and I don't think I can squeeze this onto a page, so I'm going to go to one more page, which makes it an odd number of pages. I'm going to try to jam it in here. You know what, I'm just going to erase this. Give myself a little bit more room. And it won't be on your notes, but I wrote out the definition of velocity earlier, so you guys are all right. Let's say I want to find tangent to this vector function, r equals cosine ti plus sine t j plus sine of 2t k. All right, so what is this thing going to do? Let's think about it a little bit. Well, the cosine I plus sine j, that just goes in a circle. But then my vertical component, my up and down component, my height, if you want, is going to also be cyclic. And so it's going to be like a saddle, but it'll be like a four-way saddle because we're going twice as fast. And we can maybe do a Mathematica demo of that in class. And we wanted to find this at t equals, let's say pi over 2. Pi over 2. Okay, so what do we do? First we have to find a point. Right, and that'll be easy. We just stick in our pi over 2 to all three of these. So the x, y, z will be, well, the cosine of pi over 2 is 0, right? So the x component is going to be 0. The sine of pi over 2 is 1. And we plug in the position of pi over 2 times 2 becomes pi. The sine of pi becomes 0 again, so that's convenient. So our point becomes 0, 1, 0. Why is that? Because our position vector, which starts at the origin, will end up at 0, 1, 0 here. So that's our point. But now we need our velocity at pi over 2. So velocity at pi over 2 becomes the derivative of this. So derivative of cosine is negative sine of pi over 2I plus the derivative of sine is cosine of pi over 2j plus, let's see, derivative of sine is cosine, but it's times a 2 plus 2 times the cosine of pi over 2k, right? And we can plug this stuff in, And the sine of pi over 2 is 1, so that becomes negative I. And the cosine of pi over 2 is 0, so that's plus 0j. And cosine of pi over 2 again is, let's see, negative 1. Oh, that's 2 times this, so I forgot that. Yeah, this is this. I'm just gonna make this adjustment here. It'll show up in your notes, and nobody will ever know the difference. So I'm not going to take the time to edit all this stuff out. I'm human, right? The cosine of pi, because it's 2 times pi over 2, will give me minus 2k. Okay, so my tangent line then right, this is my tangent vector. My tangent line, and remember, my vector could be anywhere in space, but I'm going to affix it to this, which makes it a unique line. So my x is going to start at 0, right? My starting point is 0, and then it goes in the negative direction, so x equals negative 1t. My y starts at 1, and then, oh look, it doesn't, the direction doesn't depend, right? There is no j component to my direction, so it's just going to stay y equals 1. And then my z starts at 0, and for every increment in t I do, it goes down 2, so the z goes to negative 2t. So now this is actually a line which is tangent to this curve, or this particle's path up here, at the time pi over 2. Okay, so that's it. That is our, we've put our toe in the water of vector calculus here, and I hope that made sense. Please think about this and come to class armed with some excellent questions. I look forward to seeing you guys.